What if the most powerful farmer on earth never sleeps, never makes a mistake, and can manage 10,000 acres without ever touching the soil? One machine today can scan an entire field, detect diseased plants down to the square centimeter, and apply treatment only where needed, cutting chemical use by 60%. Another drives itself through the night, harvesting crops with zero human input while its owner sleeps. Forget everything you think you know about farming. This is no longer about tractors and plows. This is about artificial intelligence, satellites, and robots that are quietly replacing human hands across every continent. 80 of the most advanced agricultural machines ever built are on this list, and the ones at the top will make you question whether farming as we knew it still exists at all. The number 80 on this list is already more advanced than most machines built just a decade ago. But the real shock starts when you reach the robots that have been quietly working in actual fields since 2022. At CES 2025, John Deere revealed second-generation fully autonomous tractors, orchard sprayers, and a remote dump truck called Dusty, all designed to run without drivers using advanced camera, LiDAR, and AI systems. Farmers had already deployed first-generation autonomous John Deere tractors since 2022 for planting preparation, and the company aims for fully autonomous corn and soybean systems by 2030. That is not a concept. That is a machine already working on real farms right now. But autonomous tractors are almost old news compared to what comes next. The FarmWise Titan is an autonomous weeding robot that uses machine vision and artificial intelligence to identify crop plants and eliminate weeds without a single drop of herbicide. FarmWise has deployed the Titan across conventional and organic romaine, celery, cauliflower, cabbage, radicchio, and broccoli fields. The machine rolls through rows at tractor speed, its AI processing thousands of images per second, distinguishing a weed from a crop plant with surgical accuracy. One Titan replaces the labor of over 30 hand weeders per day. Then there is the Eco-Robotics AVO, a machine that looks almost too simple to be revolutionary. AVO performs autonomous weeding operations in flat fields and row crops, using machine learning to detect and selectively spray weeds with a microdose of herbicide, with centimeter-precise detection of individual plants. The AVO robot is powered by solar energy with interchangeable batteries, allowing it to work up to 10 hours a day and cover up to 10 hectares. The field does not know a machine passed through, only the weeds do. It uses 90% less herbicide than conventional sprayers. Strawberry picking has been considered one of the last frontiers for agricultural robots because the fruit bruises easily, hides under leaves, and grows at unpredictable angles. That barrier is now breaking. The Tortuga harvesting robot uses advanced AI and dual-arm precision for autonomous strawberry and grape picking, operating 24 hours a day and picking directly into sales containers. Equipped with skid steering, it navigates fields independently without relying on GPS or wireless signals, performing full turns in place and operating seamlessly through rows. The fact that it packs directly into sales containers means zero additional handling. The fruit goes from the plant to the shelf without a single human touch. AI-powered farming robots today can analyze and process up to 500,000 plant images daily for precision crop management. That number is not a projection. It is a current operational figure. A single robot sees more of a field in one day than a human agronomist could examine in an entire season. This means no two passes through a field are identical. The machine learns, recalibrates, and improves with every row it covers. Robots equipped with machine learning algorithms can adjust their harvesting technique based on the ripeness of individual crops in real time, reducing waste and adapting their movements continuously based on live data. What makes this generation of field robots categorically different from anything built before is not just their speed or their sensors. It is the fact that they operate as systems, collecting data, feeding it back to a central AI, and improving every machine on the network simultaneously. One robot's mistake in a field in California becomes a lesson for every other unit operating in France, Brazil, and Australia on the same day. The learning never stops and the machines never tire. Harvesting is the most time-critical moment in farming. Miss the window by 48 hours, and an entire season's work rots in the field. That is exactly why autonomous harvesting machines are not a luxury. they are becoming a survival tool for modern agriculture. The agro Fendt Ideal Combine Harvester runs on what the company calls Ideal Harvest Automation. Its onboard AI monitors crop flow, grain loss, and machine performance simultaneously, adjusting settings in real time without any driver input. The system processes data from dozens of sensors across the machine every second, making micro adjustments to the threshing drum, the cleaning shoe, and the header speed. A human operator reacts to problems. The Fendt Ideal prevents them before they happen. The Case IH Axial Flow 9250 AFS Connect Combine takes autonomous harvesting one step further. It connects to the AFS Connect platform, allowing the machine to sync with other equipment in the field, share real-time harvest data with the farm management system, and receive over-the-air software updates. The combine does not just harvest, it communicates, reports, and upgrades itself in the field. Grain loss monitoring on this machine reaches a precision level that no human operator could match manually. Sensors detect grain escaping through the cleaning system and immediately trigger corrections. Over an entire harvest season, that precision translates directly into thousands of additional bushels recovered per farm. The New Holland CR Combine Series introduced IntelliSense, an automated system that continuously monitors and adjusts 16 machine parameters at once. 16 simultaneous variables recalculated every fraction of a second. The driver's only job is to steer. And even that is changing. But the most dramatic shift in autonomous harvesting is not happening in grain fields. It is happening in orchards and vineyards, where the geometry is tighter, the fruit is more fragile, and the stakes per acre are far higher. The Abundant Robotics apple harvesting machine uses a vacuum-based picking system guided by computer vision. It identifies ripe apples on the tree, extends a soft, robotic arm, and pulls the fruit from the branch using gentle suction, without bruising. The machine works at night using artificial lighting, harvesting continuously through hours when human labor is unavailable. The Wall-E autonomous vineyard robot navigates between vine rows without GPS using wheel odometry and onboard cameras. It prunes, desuckers, and monitors vine health, building a detailed database of each individual plant over time. By the third season of operation, it knows each vine's growth pattern, disease history, and yield potential better than any human worker ever could. Tomato harvesting presented a different engineering problem. The fruit grows in clusters at varying heights, partially hidden by dense foliage, and it must be picked without crushing. The Octinian strawberry and soft fruit robot solved the grip problem by developing a picking end effector that mimics the pressure sensitivity of a human fingertip, applying exactly enough force to detach the fruit without damage. Autonomous combine harvesters operating today can cover fields of several thousand acres in a single continuous run, operating through the night without stopping. The machine monitors its own fuel level, grain tank capacity, and engine performance, and either alerts the operator remotely or, in newer systems, navigates itself to the unloading point and returns to position automatically. The threshold that made this possible was not any single sensor or algorithm. It was the integration of GPS RTK positioning accurate to 2 centimeters, combined with machine learning systems trained on millions of hours of real harvest data. The machine does not guess where it is in the field. It knows its position to the width of a finger, at full operating speed, in complete darkness. What is now being tested in multiple countries is fully driverless combine operation. No human in the cab, no remote operator on standby. The machine starts, harvests, unloads, and shuts down based entirely on a pre-programmed field plan and live sensor feedback. The farmer receives a harvest report on their phone when the job is complete. Based on the research gathered, here is part 4. A single drone can spray 40 hectares of cropland in 1 hour. That number alone makes every traditional ground sprayer look obsolete, but the real story is not the speed. It is what these machines can see while they work. The DJI Agras T50 is currently the most deployed agricultural drone on the planet. It carries a 40-liter spray tank, uses a dual atomizing spraying system, and covers 52 acres per flight hour. Front and rear phased array radars combined with a binocular vision system allow it to navigate around obstacles, follow terrain contours, and adjust spray output based on flight speed, all without human input. Its coaxial twin-rotor design keeps it stable under a full 40-kilogram payload in winds that would ground most aircraft. Over 10 million acres have been treated by DJI Agras machines in a single growing season in China alone. The XAG P150 Max operates on a different level entirely. Its Super X5 ultra-intelligent control system delivers centimeter-level navigation using RTK positioning. The onboard four-dimensional imaging radar detects obstacles between 1.5 and 100 meters ahead, power lines, center pivots, irrigation infrastructure, and avoids them autonomously at night without any ambient light. The machine can survey up to 13.3 hectares in a single flight and immediately stitch the captured images into a complete field map on landing. It does not just spray, it builds a growing database of every field it touches. What separates this generation of agricultural drones from earlier models is multispectral imaging. Where a human eye sees green, a multispectral camera sees 17 distinct wavelength bands. Nitrogen deficiency shows up as a specific spectral signature 3 to 5 days before visible yellowing appears. Water stress is detectable in the thermal infrared band before the plant shows any outward sign. Fungal infection creates a measurable reflectance pattern in the near-infrared spectrum before the lesion is visible to any ground-level observer. Combining UAV and satellite data with machine learning has enhanced crop yield prediction accuracy and reduced irrigation costs by 20 to 25%. That reduction comes not from less water use across the board, but from precision. Applying water exactly where the root zone data says it is needed, on the day the soil moisture sensor says it is required. The integration of satellite imagery and drone data is where the real power of aerial farming technology becomes clear. Satellites scan fields at the regional scale, flagging zones of concern across thousands of acres. Drones then deploy to those exact zones at centimeter resolution, collecting the detailed data that triggers machine-level responses on the ground. The system works top-down: space, then air, then soil. The agricultural drone market reached $9.32 billion in 2024. By 2033, that figure is projected to reach $21.47 billion. The machines driving that growth are not toys or experimental prototypes. They are operational equipment already deployed across North America, Europe, Asia, and South America, redefining what it means to monitor and manage a crop from above. So if you thought farming was just about tractors and sweat, think again. For the ultimate upgrade, check out playprofi.com, where all the coolest AI farming tools are just a subscription away. And guess what? Today, you can snag a bonus of 500 tokens when you register through the link in the description. Who knew farming could be this high-tech and rewarding? Agriculture consumes 70% of all fresh water used by humans on Earth. That single fact explains why water management technology has become the most aggressively funded sector in modern farming, and why the machines designed to eliminate water waste are now among the most sophisticated pieces of equipment in any field. The Valley Center Pivot Irrigation System is the backbone of large-scale precision water management. A single valley pivot can cover up to 130 hectares in a single rotation, delivering water with a distribution uniformity above 95%. That is not a marketing figure. It is a measured engineering specification. Traditional flood irrigation loses between 30 and 50% of applied water to evaporation and runoff. A valley center pivot loses almost none. Integrated with soil moisture sensors and weather station data, the system calculates the exact water volume each field zone requires and delivers it on a pre-programmed schedule that adjusts automatically when rain is detected. The Lindsay Zematic Pivot takes that precision further with FieldNet Advisor, an AI-driven irrigation management platform that analyzes soil type, crop growth stage, evapotranspiration rates, and 7-day weather forecasts simultaneously. The system does not wait for a farmer to make a decision. It generates irrigation prescriptions autonomously and executes them, alerting the operator only when an anomaly is detected. One Zematic pivot managed through FieldNet Advisor can reduce water application by up to 30% compared to calendar-based irrigation schedules, without any reduction in yield. Subsurface drip irrigation represents the most water-efficient delivery method currently available. The Netafim drip irrigation system places emitters directly in the root zone, below the soil surface, where evaporation is essentially zero. Water is delivered in microdoses, calibrated to the crop's actual uptake rate at each growth stage. Netafim's systems are operating across more than 110 countries, covering millions of hectares of crops, ranging from cotton and corn to wine grapes and greenhouse vegetables. On a per-hectare basis, subsurface drip uses up to 70% less water than surface irrigation, while producing measurably higher yields, because the plant receives consistent moisture directly where its roots are, rather than depending on surface penetration. The Rivulis drip and micro-irrigation systems extend this principle to small-scale and hillside applications where center pivots cannot operate. On terraced vineyards, sloped orchards, and irregular field geometries, Rivulis emitters deliver water at flow rates measured in liters per hour, rather than cubic meters per minute. The control is absolute. Each plant receives its calculated allocation, nothing more. What has transformed these systems from efficient hardware into intelligent water management platforms is the integration of IoT sensors and machine learning. CropX is a soil intelligence platform that combines wireless in-ground sensors with a cloud-based AI to generate field-specific irrigation recommendations. The sensors measure soil moisture, temperature, and electrical conductivity at multiple depths simultaneously, transmitting data continuously to the platform. The AI cross-references this data with satellite-derived crop stress indices, local weather station readings, and historical yield maps to calculate a daily irrigation prescription for each management zone in the field. Farms using CropX have reported water savings of 25 to 50% per season, with no decrease in crop quality or yield. The most radical development in precision irrigation is variable rate irrigation, the ability of a center pivot system to apply different water volumes to different sections of the field in a single pass. The pivot moves in a circle, but each span can deliver a different flow rate, creating a variable water application map that matches the soil variability beneath it. Fields that were once treated as uniform blocks now receive customized water prescriptions at a resolution of a few square meters. A sandy patch that drains fast gets more water. A clay zone that holds moisture gets less. The machine knows the difference because the soil sensors told it, the satellite confirmed it, and the AI calculated the optimal response before the pivot completed its first rotation. A modern diesel tractor burns between 15 and 30 liters of fuel per hour at full load. Multiply that across a 10,000-acre operation running multiple machines through planting and harvest season, and the fuel cost alone can exceed $500,000 per year. That is before accounting for carbon emissions, supply chain vulnerability, or the fact that diesel prices are directly tied to global oil market volatility. The agricultural industry burns approximately 22 billion liters of diesel fuel annually worldwide. That number is now being directly targeted by a new generation of electric, hydrogen, and solar-powered farm machines. The John Deere Sesame, sustainable energy supply for agricultural machinery, was the first fully electric tractor to complete real-world field trials at commercial scale. It produces 130 kilowatts of continuous power, equivalent to a mid-range diesel tractor with zero direct emissions. The dual battery pack stores 130 kilowatt-hours of energy, delivering up to 4 hours of heavy field work per charge. That limitation is real, but it is being addressed not by building larger batteries, which add weight and compress the soil, but by developing fast-swap battery systems that allow a fully charged pack to replace a depleted one in under 10 minutes. The Fendt 100 Vario is the first fully electric tractor from a major manufacturer to enter commercial sale in Europe. It delivers 100 kilowatts of peak power and is designed specifically for operations requiring repeated start-stop cycles, front-loader work, feeding, barn operations, where electric motors outperform diesel engines in both efficiency and responsiveness. The regenerative braking system recovers energy during downhill travel and deceleration, extending operational range beyond what the battery capacity alone would suggest. The Monarch Tractor MKV is built around a different concept entirely. It is electric, but its primary selling point is not the powertrain. It is the intelligence layer. The MKV is equipped with a full autonomous driving system, a suite of cameras and sensors that map the surrounding environment in real time, and a fleet management platform that allows one operator to supervise multiple tractors simultaneously. In vineyards and orchards where rows are narrow and GPS signal can be disrupted by tree canopy, The MKV navigates using visual odometry, reading the environment with its cameras the same way a human driver reads the road. It has logged over 100,000 autonomous hours in commercial vineyard operations. Hydrogen fuel cell technology is entering agricultural machinery through a different pathway. New Holland demonstrated the T6.180 methane power tractor as a transitional step, running on biomethane produced directly on-farm from agricultural waste. The machine produces the same power output as its diesel equivalent while reducing carbon emissions by up to 80% when the biomethane is sourced from on-site anaerobic digesters. The farm becomes its own fuel producer. Crop residues and animal waste go into the digester, and tractor fuel comes out. The fully hydrogen-powered tractor concept was demonstrated by CNH Industrial, New Holland's parent company, as a running prototype. A hydrogen fuel cell generates electricity to drive electric motors, with water vapor as the only exhaust. Refueling takes minutes rather than hours compared to battery recharging, and the energy density of hydrogen means operational range is not limited by battery weight. Solar-assisted field robots represent the smallest and most distributed end of the zero-emission spectrum. The Eco-Robotics AVO, already mentioned for its precision weeding capability, runs entirely on solar panels mounted on its roof, supplemented by swappable battery packs. It requires no external power source and no fuel delivery to the field. It charges itself while it works. The economic case for electric farm machinery is shifting faster than most analysts predicted. Electricity costs per equivalent work unit are already lower than diesel in most markets. Electric motors require significantly less maintenance than internal combustion engines. No oil changes, no fuel filters, no exhaust systems, no cooling system servicing. Over a 10-year operational lifespan, the total cost of ownership for an electric tractor is projected to be 15 to 25% lower than a comparable diesel machine, even accounting for the higher purchase price. The transition is not happening all at once. Heavy tillage and long-distance transport remain diesel-dependent because battery energy density has not yet reached the threshold needed for multi-hour continuous heavy draft work. But for the 60% of farm operations that involve lighter loads, shorter cycles, and frequent stops, the electric alternative is already technically and economically competitive. The diesel engine's dominance over agricultural machinery lasted for over a century. That dominance is now ending, not gradually, but field by field, season by season. Planting a seed sounds simple. Push it into the ground, cover it, wait. But the difference between a seed placed at the correct depth, in the correct soil moisture zone, at the optimal spacing, versus one dropped 2 centimeters too shallow in dry soil, that difference, multiplied across 2 million seeds per field, determines whether a farmer breaks even or turns a profit for the entire year. The John Deere Exact Emerge planting system was built to eliminate that variability entirely. Traditional planters drop seeds using a finger pickup mechanism that introduces timing errors at high speeds, causing inconsistent spacing between seeds in the row. Exact Emerge replaces that mechanism with an individual seed meter and a brush belt delivery system on each row unit, maintaining precise seed spacing at planting speeds up to 16 kilometers per hour, twice the speed of conventional planters without any loss of placement accuracy. Each row unit operates independently, adjusting depth and downforce in real time based on soil conditions detected by sensors on that specific row. The result is a stand of plants so uniform that yield monitors later in the season show measurably reduced variability across the entire field. The Precision Planting VSET Select system takes individual seed selection one step further. Using optical sensors inside the seed meter, it identifies each seed before it is placed and can selectively skip seeds that fall outside the target size range. Combined with the V-Drive electric row clutch system, it enables variable rate planting, adjusting seeding population zone by zone across the field based on a prescription map generated from soil productivity data. High-yield zones get more seeds, low-yield zones get fewer. The machine executes a planting strategy that would take a human agronomist weeks to calculate in real time at field speed. The integration of AI into seed placement reached a new level with the development of See and Spray technology for planting operations. The Blue River Technology See and Spray system, now owned by John Deere, uses machine machine learning models trained on tens of millions of plant images to identify individual seedlings at emergence and apply microdoses of fertilizer or growth stimulant to each plant individually. The system can distinguish between 40 different crop species and their growth stages, making application decisions at a rate of several hundred per second as the machine moves through the field. Soil mapping technology has transformed the prescription that drives these planting systems. The Veris MSP soil mapping machine pulls 3 sensors simultaneously: electrical conductivity, pH, and organic matter, creating a detailed soil variability map of the entire field in a single pass. That map feeds directly into the planting prescription, so the ExactEmerge or VSET system knows exactly what the soil composition is at every point in the field before a single seed is placed. The map is not generated from satellite estimates or regional averages. It is measured directly from the soil, at centimeter resolution, hours before planting begins. The Kinze 4000 series planter integrates a load cell on every row unit, measuring the actual downforce being applied to the seed as it enters the soil. If the soil hardens unexpectedly from a compacted zone, a dry patch, or a buried rock, the system increases downforce automatically to maintain consistent seed depth. If the soil softens from a low spot or a recently tilled area, it reduces downforce to prevent the seed from being pushed too deep. This happens row by row, meter by meter, across the entire field continuously. What these systems share is a fundamental shift in how planting is understood. It is no longer a single field-wide operation with uniform settings. It is 2 million individual placement decisions, each one optimized for the specific soil conditions at that exact location, executed by a machine moving at highway speed through a field in the dark. The farmer sets the prescription, the AI executes it, and the yield data collected at harvest feeds back into the next season's planting map, making every subsequent crop more precisely placed than the one before it. The Claas Lexion 990 is the largest combine harvester currently in commercial production. It weighs 18 metric tons empty, stretches over 9 meters in length, and its header can cut a swath 36 feet wide in a single pass. The engine produces 790 horsepower. To put that in perspective, that is more power than 3 Formula One race cars combined, running continuously for the entire duration of a harvest day. It processes up to 100 metric tons of grain per hour. That is not a peak figure. That is sustained throughput, maintained across an entire field, in conditions that would shut down lesser machines entirely. The threshing system inside the Lexion 990 uses twin longitudinal rotors, each one nearly 5 meters long, spinning at adjustable speeds, calibrated to the specific crop and moisture content being harvested. The machine monitors grain loss through the rear at 1,000 measurements per second. If a single percentage point of grain is escaping through the cleaning system, the rotors adjust their speed and the cleaning shoe changes its oscillation frequency automatically within seconds, without any driver input. The driver's screen shows a real-time grain loss map overlaid on the field, so every inefficient zone is recorded for future reference. But the Lexion 990 is not the most physically imposing machine in modern agriculture. That title belongs to the Big Bud 440, a machine that was built in 1977 in Havre, Montana, and has never been surpassed in terms of raw power output for a wheeled agricultural tractor. It produces 900 horsepower from a 16-cylinder Detroit diesel engine. Its tires stand 8 feet tall. The machine weighs 95,000 pounds, more than 43 metric tons. It was built to farm the enormous wheat fields of the American Great Plains, and it still does. The same machine, nearly 50 years after it rolled out of the factory, is still working fields in Montana today. Nothing built since has exceeded its power rating for a wheeled tractor. The Challenger MT 900 series articulated tractors represent what the current generation of extreme power machines looks like. The MT 975E produces 683 horsepower, uses Caterpillar's rubber track system to distribute its massive weight across the soil, and pulls tillage implements that cover 20 meters of field width in a single pass. The rubber track design reduces soil compaction compared to wheeled tractors of equivalent weight, a critical factor when the machine itself weighs over 20 metric tons. The Case IH Steiger Quadtrack 580 is built on 4 independent rubber track units, one at each corner of the frame. Each track is driven independently, allowing the machine to maintain traction on slopes and in wet conditions where a conventional tractor would lose grip entirely. It produces 580 horsepower and pulls implements through the heaviest clay soils without wheel slip, because there are no wheels. The contact patch of all 4 tracks combined spreads the machine's weight across a surface area large enough to reduce ground pressure to levels comparable to a human walking on the same soil. The versatile Delta Track 900 is currently the most powerful single-engine agricultural tractor in commercial production, delivering 901 horsepower from a 16-liter engine. It was designed specifically for the massive grain operations of the Canadian prairies and the American Midwest, where fields routinely exceed 5,000 acres, and the planting and harvest windows are measured in days rather than weeks. At that scale, raw power is not an excess. It is a logistical requirement. One machine must cover ground that would require a fleet of smaller tractors, because the window to plant or harvest closes whether the work is finished or not. These machines do not represent the future of farming. They represent its present at the extreme end of the scale, a scale that most people never see, because the fields they work are too large to comprehend from ground level. A 900-horsepower tractor pulling a 40-meter cultivator across a Saskatchewan wheat field at full speed covers more ground in 1 hour than most European farms contain in total. The steel is bigger than most buildings, the engines are louder than aircraft, and they work around the clock, season after season, moving soil on a scale that has no parallel in any other human industry. The question asked at the very beginning of this list was simple. What is the most powerful farmer on Earth? After 80 machines, the answer is equally simple. It is not a single machine. It is the system all of these machines form together. By 2025, the global AI in agriculture market reached $11.2 billion, a 138% increase from the year before. By 2028, that figure is projected to reach $24 billion. Those numbers reflect not investment in ideas, but investment in machines already operating in real fields, on real farms, producing real food. Over 70% of large-scale farms in developed countries now employ at least one form of AI-driven agricultural technology. That figure was effectively 15 years ago. The transition from human-operated equipment to sensor-driven, AI-guided, autonomously executing farm systems did not take a generation. It took less than a decade. The scale of what these machines must accomplish is not abstract. Global food demand is projected to increase by 50 to 60% by 2050. The world's population will reach 9.2 billion people. Arable land is not expanding, it is shrinking as soil degradation, urbanization, and climate shifts remove productive farmland from the global supply faster than new land can be brought into production. The only mathematically viable path to feeding that population is to produce dramatically more food from the same land, using less water, less chemical input, and less human labor than agriculture currently requires. Every machine on this list is a direct response to that equation. The autonomous tractor that works through the night without a driver is not replacing a job for its own sake. It is covering ground that cannot be covered any other way within the available window. The multispectral drone that detects nitrogen deficiency 3 days before visible symptoms appear is not a technological novelty. It is preventing yield loss that would otherwise be unrecoverable. The subsurface drip system delivering water at the root zone is not a luxury upgrade. It is the only way to sustain crop production in regions where aquifers are already being drawn down faster than they recharge. The Class Lexion 990 processing 100 metric tons of grain per hour and the Eco-Robotics, Avio weeding a single organic field with solar power, are solving the same problem from opposite ends of the scale. One machine feeds a continent, the other feeds a community. Both are necessary. Both are already working. What makes this moment in agricultural history genuinely unprecedented is not the sophistication of any individual machine. It is the fact that these machines now communicate with each other, learn from each other, and improve collectively. A planting error detected by a sensor in Brazil is corrected in a software update deployed to machines in Canada the same week. A yield pattern identified by a combine harvester in France becomes a variable rate prescription for a planter in Argentina the following spring. The network learns faster than any individual operator ever could, and it never forgets what it learns. The most powerful farmer on earth does not sleep. It does not make the same mistake twice. It does not miss the harvest window because of labor shortages or equipment failure. It monitors 10,000 acres simultaneously, responds to changes in soil moisture within minutes, detects disease before it spreads, and plants 2 million seeds with the precision of a surgeon's hand. It is not one machine. It is 80 of them, working together, right now, across every continent on Earth. And next season, they will all be smarter than they are today.